Hello, so today we will be discussing about the motion on the inside of a smooth vertical circle. Just as an example before we start things up, you must have seen some motorcyclists in TV doing some stunts like this, okay, where he is traveling inside the circle. He will start from some point over here and then he will travel along this inside of the circle. Okay, so that is when he is completely successful. That is when the speed is very high. Okay, when the velocity is very high, then he will be able to do that. He will be traveling round and round the circle. But what may also happen is sometimes he will start from this point, he will travel up to here, and then when he reaches some point over here, he will not be having enough speed. So what he will do, he will fall down. But he won't be falling down directly, he will be falling down in this way. Okay, so this is when he is unsuccessful and he will also hurt himself in the process. Another case, what will happen is sometimes he will travel from this point, but he won't be achieving enough speed. So what he will do, he will only be reaching this point somewhere over here, and then because he doesn't have enough speed, he will come back down along the same path. Okay, so this is the case when he won't hurt himself, but again he won't be able to travel around the circle. So we will be having three cases. The first case is something like this, when he is not successful but he will come back down safely. The second case is when he goes up to this point and then hurt himself in the process, again not successful. And the third case is when the velocity is really high and traveling round and round. So overall, three cases. So we will be investigating such kind of a motion. Okay, so let a particle, and over here we are calling it a vertical circle because the circle is it's vertical. Okay, what I mean to say is we are not having a circle on the ground like this. Okay, but the circle is actually like this. Okay, so I hope that is clear. So that is why we are having a vertical circle. Let a particle starts from the lowest point A of a smooth vertical circle. And because he will be starting from this lowest point, he will be needing some velocity. So with velocity u. Okay, so the initial velocity at the point A, which is the lowest point, is u. A dash, it is the highest point. Okay, we can imagine something like this at the center. The radius of the circle is A. Okay, let A be the radius of the circle. Okay, you can even denote it with R, no problem. Okay, but I am comfortable using A. Since we are investigating the motion, again we will have to use tangential and normal directions. So what we will do over here, okay, we can imagine this imaginary line, okay, joining the highest and the lowest point, the diameter. At any point P, the forces are mg, which is the weight which is acting vertically downwards, and the normal reaction R. Again, we will be using tangential and normal directions. Again, I repeat, the particle is traveling from A towards this point, at this point P. These are the forces. We will be resolving everything along the positive tangential direction. And this one, let us call it the positive normal direction. Okay, so now that we have done it, okay, we will have to resolve the forces. Since we will be needing the component of the forces, let this angle be theta. If this angle is theta, we can easily prove that this angle will be 90 minus theta. So mg, if you resolve it towards this part, it will be mg sine theta. And if you resolve it along this direction, it will be mg cos theta. Okay, so you can write it down. The forces experienced are mg, experienced by the particle, at P are mg and r. Okay, but we are resolving it into the tangential direction and normal direction. Okay, so this is what we will get along the tangential direction. The tangential direction we will be having, this is the force that the particle is experiencing in the positive tangential direction, which is minus mg sine theta. Okay, so this is the force experienced by the particle. It will be minus mg sine theta. Mg sine theta is along this side, so if you resolve it to that side, it will be minus mg sine theta. We can cancel it. We can even write this one as v dv ds. Okay, so over here, if you notice this equation, it is having three variables. The velocity, it differs, okay, at each and every point. S, it is the arc length. The arc length, we will be measuring it from A. So at this point P, it is having an arc length S. So you can see at different points, it will be having a different arc length. And theta also, it is different. Again, we are measuring everything from the lowest point. So theta, again, we are using this line as the initial line. Okay, so when the particle is over here, then theta will be 90 degree. When the particle is at A dash, the angle will be 180. I'm saying that just to highlight that we are measuring everything from the lowest point. So we are having three variables. We will convert this one into two variables so that we can separate them. We can easily write this one as dv, d theta, ds. Okay, but again, okay, you may say that this will have three variables, but what we can do, we can actually convert this one. Okay, remember s, theta, and a. Okay, remember that equation, theta equal s by a. So d theta ds will be 1 by a. S equal a theta, so d theta ds will be 1 by a. So we have managed to convert this one into dv d theta. Okay, I will write it down directly, minus ag sine theta into a. D theta ds is 1 by a. So we can do it like this, d theta. So this one will be d theta. Now what we can do, since we have separated the variables, we can integrate them. Okay, a and g, they are constants, so we can take them outside. So we will be having something like this. Now we can integrate. We can write it as v squared by 2 equal minus ag. Over here, sine theta integration will give you minus cos theta plus a constant which we will denote as c1. Okay, I won't be needing that circle anymore. V squared by 2. Okay, so we can multiply throughout by 2, so we will be having 2ag cos theta. Over here you will be having 2c1, we can simply replace it with plus c. How will we find this constant of integration c? We will use the initial conditions. At a, at the point A, the lowest point, theta was 0, and the velocity, it is starting with velocity u. So v squared, so u squared, it will be equal 2ag plus c. Cos 0 will be 1. Plus c will be u squared minus 2ag. What we can do now, we can substitute this c over there, hence v squared it will be 2ag cos theta plus u square minus 2ag. Simply we can write this one as u square plus 2ag cos theta minus 1. So this is the expression for the velocity, which is the expression for the velocity and it is depending on theta. Okay, it is depending on theta. Okay. This one we got when we were having the positive tangential direction. Now we will use the positive normal direction along the positive normal direction. Okay, so this one, it is the force v square upon rho. Okay, this one is the normal acceleration. It will be r minus mg cos theta. How did I get this one? Again, if you are seeing the picture, okay, that I had erased, the normal reaction was along this one r, and mg cos theta was somewhere pointing in this direction. So if you make them point towards the positive normal direction, which is this side, it will be minus mg cos theta. Okay, but for the circle, the radius, okay, we can simply replace this one by a. Okay, so we can also find out what is r. Okay, I will just write this expression for the velocity here. Cos theta minus 1. Okay, so just name this one as equation 1. Okay, I will be needing that again. Okay, so over here r will be mv square by a plus g cos theta. So v square by a, we can use this one, so you will be having u square by a plus 2ag by a will give you 2g cos theta minus 1 plus g cos theta using 1. So this one we will be having m, okay, we can simplify it, u square by a, okay, 2g cos theta, so we will be having 3g cos theta minus 2g. Okay, so this is what we will get. Okay, just name this one as 2. Okay, so why exactly am I finding the velocity and why am I finding this r? Okay, because if you remember, we want to discuss 3 cases, and the 3 cases will depend on v and r. How exactly? Okay, let me just explain. Okay, remember that when the particle loses contact with the circle, okay, when he has fallen out, then that happens when there is no longer a normal reaction. Okay, because the normal reaction only happens when the particle is in contact. So when it loses contact, r will be equal to 0. Otherwise, it will have some value which is positive. Similarly, the velocity, okay, the velocity, if it is high enough, then it will be traveling. So everything depends on v and r. Okay, let me just write down this expression for r over there. Okay, so r, since we will be needing it, u square upon a minus 2g plus 3g cos theta. We just name this one as equation 2. Okay, so now that we will, what we will do is we will discuss the 3 cases. 3 cases. Number 1. Okay, but before this one, so before we discuss the 3 cases, just notice when v equal to 0, when v equal to 0, so over here you will be having u squared plus 2aj cos theta minus 1, it will be equal to 0. So we will be having cos theta, it will be 2aj minus u squared. Okay, how much will we get? Cos theta minus 1. Cos theta minus 1 equal minus u square by 2aj. So cos theta will be 1 plus this. Cos theta will be 1 minus u square by 2aj. So just name this one as a. Okay, since we have already used a somewhere else, let us name it as x. Okay, and the second part is when r is equal to 0, when the particle loses contact, what will happen? When r is equal to 0, so from equation 2 we will be having u square by a minus 2g plus 3g cos theta, it will be equal to 0. So what will happen? 3g cos theta will be equal to 2g minus u square upon a. So cos theta, we can divide the whole thing by g. It will be 1 by 3 2 minus u square upon ag. Okay, we can divide the whole thing, then we will have this. This is when the particle loses contact. This is when the particle loses its velocity. Okay, so let me just write these two things here. Okay, cos theta 1 minus u square upon 2ag. This is x, and another cos theta that we are having, this 1 by 3 2 minus u square by 2ag. Some of you may be thinking that okay, we can equate this cos theta and this cos theta, but we cannot do that. Okay, we cannot equate them, that since they are the same left hand side then the same right hand side. Okay, we cannot do that because this cos theta we have obtained when the velocity is 0, but this cos theta we had obtained when r is equal to 0. So the conditions are not the same for both of them. Okay, so we cannot equate the right hand side. Okay, keep that in mind. So this one is when v is 0. This one is when r is equal to 0. Okay, so now we will discuss three cases. What happens in the first case? The first case, remember that we are going to discuss what is happening. Okay, the particle is traveling upwards but does not have enough velocity. It will come back down. It will come back down. Okay, so what will happen is, over here the velocity at this point it will be 0. Okay, because if it still has some velocity, then it will be traveling upwards. So velocity will be 0 over here. It is traveling but coming down. But again, since the particle never loses contact, so r, it won't be equal to 0. Okay, so velocity becomes 0, but r does not become 0. Okay, this is the first case. Okay, but never loses contact. The velocity becomes 0, but the particle always remains in contact with the circle. So what will happen? Okay, so so over here what can happen is theta from x, it will be smaller. Okay, since it will become 0 first, the velocity becomes 0 first, so that's why the angle will become 0 first. Okay, and also it will be smaller than the angle theta from y. Okay, so this is the smaller sign. What will happen here is cos theta from x, it will be greater than cos theta from y. So cos theta from x, it is 1 minus u squared by 2ag. This is greater than 1 by 3, 2 minus u squared by 2ag. So what we can do, okay, we can simplify it. 3 minus 3u squared by 2ag is greater than 2 minus u squared by 2ag. 3 minus 2 will give you 1. And over here 3, 2u squared by 2ag. 3 plus 1 will give you 4. Okay, so just take this one to this side, it will give you 3. Okay, just let me write it down. 3 minus 1, 3 minus 2. 3 minus 2 will be greater than minus u squared by 2ag plus 3u squared by 2ag. Okay, so this is what is happening. Sorry, this one, I made a mistake with this equation y. This one should be only ag. This one should only be ag, that's why. Okay, so theta from x u squared by 2ag. Okay, so this one is only ag and this one is 2ag. Okay, so what will happen here is 1, it will be greater than this. Okay, we can take down common 3ag, sorry, 2ag. Then we will be having minus 2u squared plus 3u squared. So we will be having 1 will be greater than u squared by 2ag. Okay, well, why are we deriving all this? Because if you remember, everything depends on the initial velocity. If the initial velocity is not huge enough, then the particle will come back down. Okay, everything depends on the initial velocity. U squared will be less than 2ag. Okay, if you simplify this one, you will be having this. Okay, let us just call this one as case 1. Okay, u squared is less than 2ag. So cos theta from x cos theta, well, it will be less than 1. Okay, how do I know that it will be less than 1? Because u squared, it is less than 2ag. Okay, so it will be less than 1. Okay, so if cos theta is less than 1, so it says it will imply that theta, it will be less than pi by 2, because cos 90 it's 1. Okay, so what will be happening over here when the velocity becomes 0 before r? Since we are measuring from theta over here, theta equal pi by 2 will be somewhere here. So when the velocity becomes 0 first, what will happen is it will become 0 at a point theta which is less than pi by 2, maybe somewhere here. Okay, and the velocity, it is less than 2ag. Okay, so keep that in mind. Okay, it will never cross. If the velocity becomes 0 first before r, then it will never cross this horizontal diameter. Okay, it will only reach up to this point or this point, but will never cross. Okay, so that is the first case. Now let us take a look at the second case. Again, u squared less than 2ag. Okay, this is the first case. The second case that we will be discussing is r vanishes before v. So what is happening over here? Again, just remember that we are doing something like this. A particle is moving on. It will lose its contact at this point. Okay, so that is why R will become 0. Since it loses contact at this point, will become 0. But since the particle will be traveling down, so that's why it will also have some velocity. Okay, so R becomes 0 before V. So what is happening here? So if R becomes 0 before V, then theta from Y, it will be smaller than theta from X. Theta from Y, so we can have that cos theta from Y, it will be greater than cos theta from X. Okay, cos theta from Y, which is 1 by 3, 2 minus u squared upon AG, it will be greater than 1 minus u squared upon 2AG. So this is what is happening. So again, we can simplify it. We will find an expression for the initial velocity for some conditions. So we will be having, take this to this side, 3u squared by 2AG minus u squared by AG is greater than 1. So again, if you simplify this one, you will be having 2AG u squared greater than 1. That is u squared, it will be greater than 2AG. Okay, so this is what is happening. If u squared is greater than 2AG, then it will be traveling up, and R vanishes before V. Okay, but since, okay, so this is what is happening. Okay, so this is the second case. Third case, let us see. R and V never vanishes. If R and V never vanishes, that means that it will never lose contact and V will never become 0. So that is why the particle will keep on moving. Okay, so this is the third case. So for this to happen, okay, so if R and V never vanishes, so R will never become 0 even at the highest point. So even at A dash, V square will be greater than 0. Okay, so even at the highest point, the velocity will be greater than 0. I've just included the square just in case it is negative, but the square will always be positive. But it won't become 0. Similarly, R will be greater than 0. The normal reaction will always be greater than 0. Okay, so from 1 and 2, from 1 and 2 we will be having u squared plus 2AG cos theta minus 1. But theta, so even at A dash, that is theta equal pi. Okay, theta equal 180 because we are measuring everything from A. At A dash, the angle it will be 180. So theta is equal to pi. Okay, so cos pi minus 1 will be greater than 0. That is u square cos pi, it will be plus 2AG. Cos pi, it is equal to minus 1. So u square u square will be greater than 4AG. Okay, so this is what is happening. Okay, from 2, okay, we are almost done. From 2, R, it is greater than 0. R is greater than 0, so u square by A minus 2G plus 2G cos phi. It will be greater than 0 even at the point A dash. Minus 2g minus 3g cos pi So what is happening over here is that u square will be greater than 5ag. Okay, so what is happening? R will be greater than 0 and v square will be greater than 0. Okay, we are using the word and. Okay, this is when v square is greater than 0. This is when r is greater than 0. For both of them to happen at the same time, because we are using the word and. So ultimately, we have to take the greatest one, right? If we have to take in common, when r is greater than 0 and v square is greater than 0 at the same time, we will be taking the higher number, which is 5ag. So u square is greater than 5ag when r is greater than 0 and v is greater than 0 simultaneously. Okay, so this is what is happening. Okay, so this is what is happening. So we can conclude. Conclusion. Number 1, u squared is less than 2ag, then v vanishes before r. If v vanishes before r, and the particle will oscillate. The second one, u squared, it's greater or equal to 5ag, even when it is equal, okay? Even when it is equal, the particle will keep on moving. That is, it will describe the full circle. The third case, it is in between. 2ag is less than u squared, it's less than 5ag. Then r will vanish before v in the second quadrant. This is happening in the first quadrant. Okay, v vanishes before r in the first quadrant. This is happening in the second quadrant, and it will describe the full circle when u squared is greater or equal to 5ag. Just for you to not make any mistake, we are seeing the first quadrant because usually you are taking this one as the first quadrant, this one as the second, third and fourth. Okay, this we are taking it in this way because when we are measuring it from this line. Okay, but since over here we are measuring it from the point below, so what is happening over here? We are taking this one as the first. In our case, in the motion of vertical circle, we are taking this one as the first quadrant, this one as the second, this is the third, and this one as the fourth. Okay, so this completes this investigation of the motion inside of a smooth vertical circle. Until next time. But before that, you must remember that you must try to remember the expression for the velocity and for r. Okay, equation 1 and 2, they are very important, so try to remember them. Until next time.